All right, so the second handout, we didn't quite have enough time in class to get through it all, and so I just want to get to the main points of what I'm talking about. But also, there are these videos, so if you go and watch that, hopefully this sort of, is consistent with what you get from it. But exponential growth is the idea that the next y value, that's what I'm going to call this, the next y value. It's sort of hard to refer to an idea like this with English words. We sort of need math words, and that's what I'm trying to say when I say this stuff, okay? So the next y value is proportional to, okay, there's this vocab word that keeps popping up, the current y value. So what proportional to means, it means, so here's that next y value, it's going to be equal to, and here I use C, I should have used B, because I use B everywhere else, okay? It's proportional to some number times the current y value. And this number stays the same, no matter what t is. So for example, if t was 0, and let's go ahead and take a look at this little experiment here to demonstrate the general rule that we're seeing here. If we treat this like a science class, then we run some experiments. So a bacterial population begins with 3 bacteria. So when time is 0, the population at time t, so the initial population when time is 0 is 3, and then it doubles every hour. Okay, so 1 hour later, sorry, at t hours, okay, 1 hour later, well, what's the population? Well, this number has to double. The next y value is proportional to the current y value. So I'm trying to write down the next y value, and so here's the current y value. And if we drew a picture of this, right, I have 0, 3, and here's 1, and so what's the next y value that I use? What should it be? Well, it depends on this current y value. And it's going to double every hour. So 1 hour later, I should double that 3, and I should get 6. So 1, 6, okay? But I'm going to write that as 3 times 2, okay? We can agree 6 is 3 times 2. And the reason I'm writing it like that is because ultimately, what this question asks for is for us to find a function for p of t. So I'm trying to figure out what this function is. We should be able to, if I ask in 20 hours, what's the population, like what goes here, So, all right, let's get a feel for that function. Okay, another hour goes by. Okay, so now we're at hour 2, and the population has to double again, right? Every hour, this population doubles. So the 6 becomes a 12, but again, I'm going to write that as 3 times 2 times 2, okay? And another hour goes by, and so we're up here at 12, and now we're going to be up here at, and so notice this vertical jump, okay? That vertical jump is growing. We're jumping higher and higher each time, and that's the fundamental property of exponential growth or exponential decay. It's that this jump, so here's what the jump is, okay? The jump is a difference between 2 y values. These are y values. This is y2, this is y1. Right, so for example, let's take a peek at this. I want this to make sense. If t was equal to 2, then what this boxed thing is saying, so p of t plus 1 minus p of t, we plug in that t is equal to 2. We have p of 2 plus 1 minus p of 2. And, okay, caution, this is not, okay, this is not p of 2 plus p of 1 minus p of 2. P is a function. And so I don't know what that function is, but for example, if p of t was the square root of t, okay, if that was the function, then p of 2 plus 1 would be saying the square root of 2 plus 1. And famously, that is not the same thing as square root of 2 plus square root of 1. You can try and recalculate it. It doesn't work, okay? You cannot distribute a function evaluation almost ever. The only time you can ever do it is if your function happens to be multiplication by a number, okay? So what do you do? What do you do? Well, you can think of this like order of operations where you have to do parentheses first. This is saying find the population at hour 3, subtract the population at hour 2. Okay, the population at hour 3, what's that? That's 3 times 2 times 2 times 2, right? Because I had a double. I had a double to get here. So, oh gosh, all right, this one was 12, so this one must be 24. Okay, so here's 24. So the population at time 3 is 24. The population at time 2 is 12. Okay, so this boxed expression is this vertical jump here. It's size 12, and where that comes from is a difference in y values. This y value is 24, this y value is 12, and 24 minus 12 happens to also equal 12. So like that's where that one comes from. But anyway, this vertical leap, the change in y values, it turns out is also just proportional to where you are. So exponential growth is when the next y value is proportional where you are, or you could say the change in y values is proportional to where you are. And notice the constant of proportion changes. Okay, that's just from algebra. Like I literally just subtracted p of t from both sides. And so I'm going to talk a lot about option 1, okay, which is just to say the next y value, let's do it again, the next y value is proportional to the current y value. So the next y value has an x value or t value when t is 4, and this next y value is twice as big as this previous y value. All right, so this is unnecessary to copy and paste here. I could have just written it down, but I just like really want to emphasize, like, you know, we are taking the old y value and we're multiplying it by 2. Okay. All right, so do you see some kind of pattern forming? In fact, do you see some kind of relationship between like the number over here and how you might compute the number over here? Let's sort of stare at it for a while. What's something that we see happening? What's something that maybe, you know, is there a pattern occurring? And it looks like if, say, t many hours go by, so like maybe t was 20 or something like that, then the way you would compute that is 3 times 2 to the 20. It looks like the t value corresponds to the exponent. And in fact, it does. Okay. So for t, we would get 3 times 2 to the t. Okay. So our goal was to find a function p of t. So I'm going to say it's 3 times 2 to the t. And you could test this, okay, by plugging in t values. What's p of 1? Well, it's 3 times 2. Is that what I'm supposed to get? Yes, that's what I'm supposed to get. And that's why I didn't bother simplifying, because you can very clearly see that it works, right? If you change t to be any of these, you'll see you get the correct number of 2's, right? That's what's changing. Okay, so now maybe we can also see why this is called an exponential function. It's because this thing here appears in the exponent. But, you know, despite the name, the property that's just really interesting is that the next y value is proportional to the current y value. In fact, this only happens for exponential functions. This is unique to exponential functions. So when you see this occurring, you automatically know something about p of t. So I say I want us to figure this out. I'll give us the answer of what goes here. So p of t is going to be some number times, and then this factor here, b to the t. Okay, so what's the number that goes right there? It's whatever the initial population or whatever is. So see how when time was 0, we had 3, right? And that's because, so, like if I plug in 0 for t, I have 3 times 2 to the 0. And famously, anything to the 0 is 1. So this is the same as 3 times 1. I get 3. When no time has gone by, there's no time for this exponential growth to occur, or there's no time for exponential decay to occur. It's just the original amount. So the form that you're going to see on future formula sheets and stuff is going to look kind of like this. It's going to say P0 times b to the t. And don't let this P0 trip you up. It's just the original population, or whatever you'd get if you plug in t equals 0. That's like literally what they're trying to say here. Okay? All right, so when we talk about exponential functions, this is like what I want you to know about them. It's that the next y value, right? I don't know how to say in English what I'm trying to say in math. Here it is in math. And if you know math and you speak math, and it is its own language, then this is like super clear. Boom, done. It means this equation is true, okay? And this equation right? We just saw it over and over again in this table, but just to write out some examples, it's saying P of 1 is equal to B times P of 0, or P of 2 is equal to B times P of 1, or P of 3 is equal to B times P of 2, right? All of these things are saying the same thing. It's that, you know, P of t, whatever t is, whether it's 0 or 1 or 2, if you multiply the population at that time times B, you'll get the population next year, or next hour, or next minute, however we're measuring time, okay? All right, this is the defining property of exponential functions, okay? Wild. All right, so population growth is a classic example of why exponentials occur, because, like, the new population is proportional to the current population, because the current population tells you how many people there are possible to make babies. And so then if you have some kind of growth rate, then, you know, your new population, okay, B is not quite the growth rate. Really, this form is a little bit better for this. But your change in population, sorry, not that one, it's this one, your change of the new population minus the current population, that's how many new babies there were, right? Well, that has to do with how many people there are able to have babies. So in fact, this is your growth rate, but whatever. Or your birth rate, I should say. Okay, the point is the amount of new stuff is proportional to the amount of current stuff. And this happens all the time with population growth. It also happens in finance. So now we're going to look at exponential decay. So if inflation is 8%, what that means is if you have $1, okay, and a year goes by and inflation is 8%, then it loses 8% of its value, okay? So if another year goes by, the wrong answer, okay, what we don't do is we don't subtract another 8%, because this first arrow is not subtraction. This first arrow is actually multiplication by 0.92. And so in fact, you're going to get 0.92 squared. And then you're going to get, so this is all like a year goes by, a year, a year, a year, and you're going to get 0.92 cubed, okay? Because, so inflation being 8%, what it's saying is the value next year is equal to 92% of the value currently, of the current value, I should say. We'll do that, okay? Current value, okay? So, all right, when I have $1, 92% of that is 92 cents. But when I have 92 cents, 92% of that is 92% of 92%. Okay, so, and then it just keeps going. Okay, I'm lying a little bit, but like this is essentially the idea. And in fact, after t years, $1 would be worth $1 times 0.92 to the t. Right? And there's nothing special about the number 1. If you have $50,000 in savings, 50,000, and you just let it sit in savings, and so in this problem, okay, I just chose numbers to have a net inflation. If the savings account gives you 2% interest, which often doesn't happen, often the interest rate is like 0.01%. Okay, it's abysmal. So for all intents and purposes, a savings account is kind of like just having money under your mattress. So for experiment 2B, I really should have just taken 2A and just said how much, so forget about all this, all right? Let's just, how much would $50,000 be worth in 50 years? Okay, 50 years. Well, you have to do 0.92 to the 50th power. And in class, someone computed that, and they said it was $773, and I don't really care about how much cents there is, okay? So now your bank account won't show $773. Your bank account will show something bigger than $50,000. But because of inflation, the buying power of that $50,000 is as if you only had $773. So that's because a savings account will never give you a decent percentage. It won't match inflation. The bank doesn't want to lose money like that, right? So anyway, and this is also why, you know, if you're comfortable with exponential growth, if this it doesn't quite make sense, but it piques your interest, here's why it should pique your interest. It's because the society we live in does not mandate that, You know, okay, if you work for a certain amount of time, or even just, God forbid, that you exist is good enough, but whatever. If you work for a certain amount of time, then you will have your basic needs met in retirement. No, no, no. That's not what they say. They say you have to save. Okay? But see, saving is rigged against you because inflation, look, 8% is high. Okay? Typically, maybe it's like 3%. So if we were to do something more realistic, I think we could even just do 2%. Okay? If we do 2% inflation over 50 years, then it's this equation. So let me just get my computer really quick and let's just run this. So I'm going to go 50,000, 3 times 0.98 to the 50. And it's about $18,000. Okay. Oops. Wrong thing. There we go. It's 18,208. Okay. I'm just going to say it's about $18,200. Okay. So if you work your butt off this year and you had a surplus of $50,000, you put that in the bank and you say, gosh, I'm saving for retirement, baby. Well, 50 years from now, the buying power of this is as if you had only saved up 18,000, and that's what you had in that moment. Okay? Money is less valuable as it moves into the future. And so this is why saving for retirement is kind of cruel. So then they say, oh, well, what you should do with this money instead is you should put it in the stock market. See, if you put it in the stock market, then even though inflation is 2%, on average, the stock market returns something like, I don't know, 6%. Okay. So then you're gaining. Then it's 0.04 to the 50. Okay, and notice this number is bigger than 1, and so this will grow. And while that's kind of true, but, you know, what stock are you putting in? Does it happen during a recession? God, there's been like 3 of those in my lifetime, and that would greatly influence. Well, whatever. So, you know, instead we make it a gamble, and that's how they justify it, when we could just guarantee basic needs. But whatever. The point I'm trying to make is, the more fluent we are in mathematics, the better we can understand public policy and form an opinion on how retirement should be handled, for example. But okay, whatever. So exponential growth or decay has the property that the next y value is some multiple of the current y value. That's why these powers, 1 becomes 2, becomes 3. That's why there's an exponent here. It's because as t increases, in fact, look, let's just see what happens. If I plug in t plus 1 into my function, p of t, I'll have to plug it in over here. This is some number times b to the t plus 1. And gosh, well, if I pull out a b, that's going to pull out this 1. So I have a b times c times b to the t. Right? So this 1 is why I have a b here. And notice, sitting right here, what is, I don't know what that is. Sure, I'm done. Sitting right there in the box, that's p of t, right? P of t, what is it? Well, it's c times b to the t. This is c times b to the t. And you can just see, like, okay, whatever that population was, if I multiply by b, that'll be the next population. So anyway, okay. When someone says an exponential function, this is an exponential function, just like when someone says a line and you think y equals mx plus b, right? You sort of know, oh, I need a slope, I need a y-intercept. Okay, you need a base for your exponent, and you need an initial value, right? This is p of 0. If you plug in 0 for t, it kills this, it becomes 1, and you just get c. So, all right, that's an exponential. Fun little factoid, okay? Not that it really matters, but there's sort of a nice relationship between exponential functions and lines. In fact, if I sort of like had e to the power that is a line, okay, this is where, okay, b was kind of a bad choice because I used b here. These are different b's. So maybe I should use, like, what's a y-intercept? Maybe y0, that could be the y-intercept. Okay, fine. So y0, okay. Well, rules of exponents says, well, this is equal to, there's a e to the y0 times e to the mt, and power to power, you can multiply the powers. So, and this is looking like, gosh, this thing is just some number, and if I call the thing in parentheses b, and hey, what do you know, look at that, an exponential function is what happens if you put a line up inside of an exponent. But whatever, that's beside the point, just some cutesy algebra stuff. Okay, so here's what exponential functions look like. We're often going to write them like this in this class, which is to say, The base is going to be fixed as the letter E, which is 2.71828. It just keeps on going forever. Okay, yeah. And instead you're going to have natural log B up here, K whatever, and C, this special number C is the same thing as P at 0, right? If you plug in T equals 0, you get C. Okay, this is a special relationship with E's and logs, and it's because they're inverse functions. The rest of the algebra trickery involves log B and, yes, and what? Well, and this fact, ln, so e to the ln of b to the tth power is the same thing as if I replace, well, okay, so first of all, I can multiply, so that's what's happening here. That's probably what I wanted, this blank. I don't know, too much time has passed since I wrote this worksheet, and where we are now. So whatever, it's rules of exponents. Okay, all right. We're going to dive a little bit deeper into this, but unfortunately I don't have like too much deep stuff to say about it. We're going to get to inverse functions eventually in this little talk here. And inverse functions are things that undo each other. So f inverse after f of x will always spit back out x. And that's the same phenomenon that's happening here. So if f inverse is natural log and f of x is e to the x, then what this is saying, if I use these two functions, let's see, f inverse is the outside thing. So I'm going to do ln as the outside. And inside of f inverse is not x. Inside of f inverse is a whole function. And in that case, that whole function is this. So I'm going to put it here, e to the x. And they're going to undo each other. This says they will undo each other. You get x, you get x. Okay. Now, similarly, when someone writes f and f inverse, then who's who doesn't actually matter. I could have written this exact same idea like that. So it doesn't matter who's first and who's second, as long as f and f inverse follow one another, they're going to cancel, and you're going to get just x. So if instead, I just erased this because I had too many scribbles, so let me just write my scribbles back down. Okay, or if the e function comes first, I have e to the, and no longer is it just x, no longer is that just x. I'm looking over here, okay. Now it's ln of x. And what's that equal to? X again, okay. That's because these are inverse functions. We'll talk a bit more about them. Let's talk about logs. Okay, it'll be an example of inverse functions, but then we'll do them in generality. Okay, so by the way, I don't know if you've ever taught that multiplication is repeated addition. This is true so long as you have integers, okay? And the reason multiplication is sort of easier than division is because the numbers tell you when to stop. If I do 3 times 5, you can either do 3 5s or you can do 5 3s, okay? But you just add them up, and either way you get 15, and that's the answer, okay? These numbers tell you exactly what to do. Okay, division's harder. These numbers don't tell you what to do, okay? But if you did not know this was 9, okay, then what you can do to sort of guess what this number should be is start taking away 2. If I take away 2 once, take it away again, 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 eventually I get 0. And then the number of times I took it away is what 18 divided by 2 is. Division is like repeated subtraction. Division undoes multiplication. Division is the inverse of multiplication. And so, similarly, subtraction is the inverse of addition. And so, there's a relationship here. It's just, okay, you have to sort of know when to stop. 0 is the magic number, and this is not actually very useful. But if this was, I don't know, 3rd or 4th grade, and I told my students, look, hey, students, I have $18, and I'm addicted to energy drinks, and every energy drink costs $2. How many days in a row can I get an energy drink? And if you're just talking to 3rd graders, they might use a tactic like this. They might say, hey, you can get it 9 days in a row. And if I was talking to 13th graders, then they might say, well, you can get it 9 days in a row because 18 divided by 2 is 9. So implicitly, you're using the same technique, right? Okay, whatever. All right, exponentials are like repeated multiplication, and the numbers tell you when to stop. Again, you know, 5 to the 3, it's 5 times 5 times 5. Great, done. You know, nothing to it. So much easier. Okay, so similar, logarithms are like repeated division. They're going to undo the multiplication, but you have to figure out when to stop. This is why they're trickier, okay? And now we care about hitting 1, no longer 0. it's a 0 exponent, right? Because it's going to be like something to the 0, and then 1 ends up being the magic number, but whatever. Okay, so when I write this, one way to figure out if, like if I took a weird thing, like log base 3 of 42, okay? So I could say, well, gosh, 42 divided by 3, what is that? Well, 42 is 7 times 6, 7 times 6, so I'm going to get 14. Okay, and then 14 divided by 3, well, gosh, that's going to be like 4-point stuff, okay? I don't need to know exactly, right? 12 is 4 times 3, and 5 times 3 is 15, so this is somewhere between 4 and 5. And 4-point stuff, if I divide that by 3, I'm still bigger than 1, but not a lot bigger. It's going to be 1-point stuff. This is 1-point stuff, okay? And finally, this results 1-point stuff. If I divide it by 3, I'm too small. I'm less than 1. I would have blown it, right? Similarly here, if I subtracted 2 again, I go past 0. I would have blown it. So what this is telling you is I count 1, 2, 3, and then a little bit more, but not a full amount more. So it turns out log base 3, it's somewhere between 3 and 4. Okay, sorry, log base 3 of 42. It's somewhere between 3 and 4 because I can repeatedly divide 42 by 3 3 times, but not 4 times without getting smaller than 1. Okay, so that's about as much as we can pin it down. Logarithms are hard. Okay, you're going to need a calculator for logarithms almost all the time, except for one special case, and that's this special case. So 125 is 5 cubed, okay? And logs are inverse functions, and it turns out that this 3 pops out because this number and this number match, and so the log and the exponents cancel and 3 pops out. But, said differently, 5 cubed is a perfect power of 5, so if I divide by 5, then I get 5 squared. If I divide that by 5, well, then I just get 5. If I divide that by 5, well, then I get 1, and this is when I stop. So how many times did I divide by 5? 3 times. It was this power. It was staring us in the face, right? We already knew the moment that I wrote 5 cubed, I could have divided by 555, and I would get 1. I would do it 3 times, right? So that's an example of these being inverses. So anyway, we don't need to really be able to compute logs in our head. In fact, I already showed you most numbers that we think of, we won't be able to, but we can just get a sense of like sort of where it falls roughly, okay, within 2 integers. Okay, so logs, I haven't really explained what they are, but I'm starting to get that sense of it. And so here's an example of how we might use logarithms without realizing we use logarithms. Just like here, a second grader might use division without realizing they're using division. Okay, so my dog Lenny, he has hip arthritis, and one day I came home and he ate his entire bottle of Galliprant, which is like, it's a doggy NSAID, which stands for non-steroidal anti-inflammatory drug. Ibuprofen is a human NSAID. Do not have 128 pills of ibuprofen. You will die. That'll be liver failure. But shockingly, Galliprant is not that toxic to the liver. And it costs $85 to talk to animal poison control. Other fun fact, because this is a real story, except in real life it was about 90 pills, but whatever. Okay, the half-life is roughly a day. That's true. You could look up the half-life of Galliprant in a dog. And Lenny normally gets 1 pill a day. Okay, so my question is, how many days go by until Lenny basically needs another pill, until he has less or equal to 1 pill in his system, right? And so you can play the game. You could do 128 divided by 2. That's 1 day going by, okay? And you'll get 64. And you divide it 2. Another day goes by, okay? And you get 32. And another day goes by. Each division by 2 is a day. So this is a +1, +1, +1. And so now he's down to 16 pill equivalents. And whoop, then he's down to 8 pill equivalents. Then he's down to 4 pill equivalents. Then he's down to 2 pill equivalents. So +1, +1, +1. Okay, but this is 1, so I'm not going to do it again. If I divide by 2 again, then I'm too small. So what is that? 1, 2, 3, 4, 5, 6, 7. And what that's really saying, by the way, is that 2 to the 7 is 128. And we're probably more comfortable with this, but that's the same as saying log base 2 of 128 is 7. Okay, log the number here, and the number here, and then there's the number here, and the number here. Okay, log is asking what power on your base equals the number in here. So log is trying to find the exponent. And that's just it. When you're trying to find exponents, you have to use logarithms. Okay, so let's look at how we typically use them in this class. This was on the last WebWork, WebWork 2. So it's typically going to be stuff like this. Okay, we have an equation like this. For example, one of the ones that is about to come up. See this baddie? So 1, 2, there's 3 zeros and a 1 0 and a 9, and then there's a t. Okay, so my k, this monstrosity is k. Okay, you can see why I don't want to put down, right? Just it's k. T is my variable. So if I was looking at something like this, then like maybe over here is a 0.35. Okay, fine, but that's playing the role of a. Okay, and we're going to want to solve for t. We're trying to solve for an exponent, and that's when logarithms are useful. That's exactly when we use them. What exponent on 2 gives me this number? Log is like saying, what exponent? Okay, and then if it had a base b on b, and if there was something here, you'd say equals the something in there. Okay, so if we know, if this is, so natural log is log base e, okay? So log base e of e to the kt is like saying, here we go, log is saying what exponent on this number is equal to this number. So in fact, let me rewrite this really quick. This is saying what exponent on this number is equal to this number. What should I put here so that way these two things are equal? It's kt, okay? So if you have the same base as the thing in here, then the exponent just pops right out. So if we were trying to find t, you would take the natural log of both sides. The left-hand side just becomes kt because these two things are inverse functions. The right-hand side is natural log of a. That's just some number, okay? Don't overthink it, some number, and then you divide by k. All right, let's do it in practice. Let's do it on this problem here. And this is how we're going to often use logarithms. Logarithms tell you exponents. Maybe I should write this in a less lazy form, so let's do that one more time. So I have log base b of, and then some number here, I'll put an a, okay? What this is saying, I'm going to color code it. So when I see the log, this is saying what power on b equals a. Okay? What power on 2 equals 128? 7. The answer was 7. Okay? All right, let's do it here. So, all right, so some amount of carbon-14. Amount, by the way, that's measured in grams. This is a mass. Okay? Amount of carbon-14 left after t years. Years, that's a time. Okay? After the death of an organism is given by this equation. Okay, fine. Now, something that's very unnatural, if you've never seen it before, is to just sort of know that Q naught is just some number. This is just some number. It's fixed, okay? Maybe it's 7. It's not 7. It's really gross. But maybe it's 7, right? And the fact that it's actually really gross is why we don't write it. In fact, so I'm going to call this part A, and I'll call this part B. Let's do part B first, so that way you can see what this disgusting number is, and why instead of showing you the number, they dress it up real nice and pretty, and they call it Q naught. Okay, so if this many grams, hey, grams, that's an amount. That's referring to a Y value in this case. So if this many grams are present, okay, is equal to, and then it'll be the equation, and hey, years, that's a t value. So we have Q naught e to the minus 0.123109 times 9,000. Boop. Okay, that's all an exponent. And in fact, this whole thing is just one number. Okay, I know. So many students, what they want to do is plug that number into a calculator and figure out what it is. You don't have to. You don't have to. Look, there's a multiplication here. Okay, there's a multiplication. This is a number. Maybe it's 4, right? Maybe it's 4. It's not 4, but maybe it's 4. And if you had to solve for Q naught, what would you do? You would divide this number over. So let's do it. Just do it. 0.035 divided by this disgusting number, e to the minus 0.000109 times 9,000. Okay? That number right there is Q naught. And that number in the box is likely irrational, which means you cannot write it as some decimal without going on forever, for the rest of time. You just can't do it. You can do approximations, okay, but you can't write down the actual number. But I can write down the actual number in theory, and here it is, right? Okay, so anyway, this number is Q naught. Now, if it's just killing you and you want to know what that number is, let me do this really quickly. So I have 0.035 divided by e to the negative 0.1230109 times 9,000, and that is equal to, let me make sure this worked out correctly. Oh, that didn't work out correctly. 1 second. Put this here. Put this here. I had a parenthesis error. Okay. So, all right, I'll just say about, because again, this would go on forever, right? 0.933492710, and it just keeps going, okay? So you can either have an infinite decimal or just write what it is. So I'm just going to write what it is. Or wait a second, just give it a name. Just give it a name. And when I say Q naught, you know I'm referring to this baddie or this baddie. It's the same baddie. All right. Sweet. So part B was to figure out Q naught. Apparently, there were this many grams of carbon-14 when this organism died. Okay? That's referred to as the original amount. Okay? The reason Q naught is called the original amount is because what happens when you plug 0 into this formula for t here? Well, it's Q naught times e to the negative 0.000 times 0. Okay? And this number, which is this number, if you multiply by 0, it's just 0. So that's Q naught times e to the 0. And now, look, if you know one thing about exponents, look, I actually want you to know like 3 things about exponents, but if you know one thing about exponents, you need to know that something to the 0 is 1. Okay, this number right here is 1. So, what is Q at times 0? It's Q0. That's why we call it Q0. Okay. It's what you get when you plug in t is equal to 0. And that's also why it's called the original amounts, because no time has gone by. Time after death, no time has gone by. The organism just died. Oh my goodness. Tragedy. And there's this much carbon-14 in them. Okay, fine. So that's what B is asking for. We know Q naught. Let's look at A. And in A, you don't need to know Q naught. That's why this order doesn't matter, okay? So A, when, wait a second, what type of word is when? That's referring to time. So it's referring to a t value. So they're saying solve for t. That's what this word is signaling to us as a reader. If word problems are tricky for you, units can honestly really help, okay? The word when is saying solve for t, do it, okay? All right, so how are we gonna set this up? So when will 1/5, or 0.2, of the original amount? Okay, so 1/5, or 0.2, of the, I prefer 1/5, sorry, it really just excites me. Okay, 1/5 of the original amount. When will this be, when will this be there? Well, so this is what you better get. This is a y value. It's a final amount. It's an amount, okay? Great. Well, that's equal to Q naught times e to the negative 0.1230109 times t. Okay, great. So this is what we're trying to solve. Now, you could take a logarithm both sides, but don't do it yet. Just don't, okay? And in general, look, this kind of hurts my soul to say, but it's a useful mnemonic, so I'm going to say it, all right? Please excuse my dear Aunt Sally. This is for if you have to simplify something. If you're simplifying something, you go this way. Simplify, okay? So for example, if I asked you to compute 1 plus 2 squared cubed, okay, then what you should do is you should first look in here, because it's inside parentheses, and you say, oh wait, there's an exponent here, so I should compute that, and then I should add 1, okay, so I have 5, and then you can cube everything and get 125, okay? All right, now look, you don't have to do stuff that way, but it's a useful mnemonic if, arithmetic is overwhelming, all right? Now, if you have to solve for something, you often go the other way, okay? Solve for. So what do I mean? So I look over here, and I'm trying to solve for t, okay? And I ask myself, is there addition or subtraction? No, there's not. Okay, fine. Is there multiplication or division? Right, I'm going this way. Oh, yes, there is. Here's a multiplication. Okay, so get rid of it. And what I mean by get rid of it is the side that has t, we want to clean it up. So I'm going to divide both sides by q naught. And notice what happens. They just go away. Now I have 1/5 is equal to e to the negative 0.1231109 times t. Great. All right, is there an exponent? Yes, there is. Okay, let's get rid of it. How do you get rid of exponents? You have to take the natural log. So I take the natural log of this, and it's going to equal the natural log of this. All right, fine. Natural log is log base e, so these two things undo one another, and the exponent pops out. So I have minus 0.1230109 times t. I think my cat is stuck somewhere. All right, so trying to get t, the natural log and the exponent, they undo one another. It's the same, like I know it doesn't seem the same, but it's the same as if I wrote t plus 3 minus 3 is equal to t. These two actions undo one another. Similarly, raising to the, having an e and putting the power there or doing the log, they undo one another, okay? I can say a little bit more. This is, right, we have log base e, so this log is saying what power of, and then this e is saying e equals, and this is saying e to the blah, blah, blah. And it's like, wait, what power of e equals e to the power? Bro, it's the power. And that's what this is saying, okay? All right, so, right, hey, look at what we have. We have a number over here. I know it doesn't look like a number. I promise it's a number, okay? It's a really gross number because it's another irrational. Just don't worry about it, right? Like, square root of 2, perfectly good number. No reason to ever write, what is it, 1.7 stuff. I don't know. Choking on my spit. Okay. So, we got to solve for t. We got a number times t. Let's move that number over. Let's divide both sides by that number. And what you get, the end result, is that t was equal to the natural log of 0.2, aka 1/5, divided by negative 0.000109. Okay, there's t. That's the answer for A. Voila. All right, let's do it again. So on the last video, although we didn't get this far in class, but this will also be in the Desmos activity, we had sort of graphed what exponentials look like when you have like b to the x, although I guess I should use a t, okay? And it's either going to look like that when b is bigger than 1, or it's going to look like that. Nope, stop it, Anthony. They have to go through the same point. It's going to look like that when b is less than 1. And what is that sweet, sweet point? Well, if b was equal to 1, that's just 1, because b to the 0 is equal to 1, right? Okay, so it looks like that. And now the thing is we want to think of 5e to the 0.75 t. We want to think of our function like this. And b is the thing in parentheses. Okay? So we should ask ourselves, is b less than 1? Is it equal to 1? Or is it bigger than 1? Here's the thing. E to the 0 is 1. So really, it's just asking, hey, this power, is it positive or negative? And let's jump here to my remark, because that's where I put it all there. This k, when k is negative, so think like e to the negative 1 times t, well, a negative k is like having it's like popping this down in the denominator, okay? And e to the t, like this thing would be decreasing. You have a small number here. It's something less than 1. It's something less than 1. It would decrease, okay? Meanwhile, if k is bigger than 0, such as, oh, I don't know, 0.75, then our function of this form increases, okay? So, there's this, asking how long does it take for this decreasing object to equal a half? That's called a half-life. Or how long does it take for this increasing object to equal 2? That's called a doubling time. So, we're over here. And this s of t function, they're curious, is it increasing or decreasing? So we look at this exponent here, and we say, well, gosh, that exponent is positive, so in fact, it's increasing, okay? And, all right, if the function is increasing, hey, it is. What's the doubling time? So, if you get lost on a test and you think, gosh, I don't know, doubling time, half-life, oh, I don't want to mess this up, don't sweat it, okay? So here's what we can do. See this 5 here? That's what happens if t is equal to 0, and this whole thing is 0, e to the 0 is 1, and that's gone, and you get 5, right? So initially, when t is 0, there's 5. If you double it, then you'd get 10, okay? 10 is equal to 5 e to the 0.75 times t. And if you find t, you would have found the doubling time. So that's one way to do it, okay? Another way to do it is to realize, like, look, this s of t function, 5 stays the same. 5 doesn't change at all, ever. To double means this thing here has to double, okay? So if we just think about this thing here, what happens when t is 0? Well, plug it in, you get 1. Let's double 1. We want 2, okay? You will get the same answer, whether you think of it like this or think of it like this. It's the same, because what do? We multiply both sides by a fifth or divide by 5, however you want to think of it. That 10 becomes a 2, and that 5 disappears, okay? And so we'd be here. And how do we solve this? We take the natural log of both sides. Why do we do that? Because natural logs tell you powers. Okay, so we have natural log, e to the 0.75t, and that's 0.75t. And you divide over the 0.75, you find out that t is the natural log of 2 divided by 0.75. Okay, cool. That's the answer. That's the doubling time. What if you messed it up? What if you were thinking it was a half-life? What if you did 1/2 is equal to e to the 0.75t? Okay? If you did all the same work, you would find t is equal to the natural log of 1/2 divided by 0.75. And these two values differ by a minus sign. And it's because 1/2 is 2 to the minus 1. There's some other rules of logarithms. Okay, you can think of it like that. But here's what I have to say. If you're stuck on a test and you don't know half-life or doubling time, you can find both. Punch them into your calculator. One of them is positive. That's the one we want. We want time to march forward until the sad death of the universe, okay? But if we could march time backward, maybe that'd be cool, but we can't. So anyway, if you don't know which one makes sense, you could always just find them both. The positive one is the answer, all right? Okay, cool. Sweet. I'm going to skip this, but I'll start with the setup, which is s of t is equal to that. Okay, so here's that, and we need to set it equal to s of t. S of t is that equation, so that's 5e.75t. And so you solve for t. What do? You divide the 5 over, you take a natural log, you divide the 0.75 over, dope. All right, cool. That's my dog. He's very vocal. All right, look, logs appear in life when things are, that shouldn't be very, I'm so sorry, when things are not sensitive to change. Okay, so an example is pH. So pH is the negative log of the molarity of hydrogen ions. Okay, let me show you what I mean by not sensitive to change. Okay, if the number of hydrogen ions doubles in a solution, okay, if I snap my fingers and it doubles, or if I'm comparing two solutions and this solution has a molarity of H, I'll call it, and this solution has a molarity of 2H, right? Okay, what's the pH? How do they compare? Well, I don't know. I'd have to take a log base 10 of this bad boy, and I'd have to take a log base 10 of this bad boy. And this all just comes down to rules of logarithms, which you're sort of just like expected to know. There's a link to Paul's online math notes and last web work. There's so many rules you can learn, and it just becomes cumbersome, okay? But the log of a product is the same as adding the individual logs, okay? And the reason for this is the same reason as the fact that a to the x times a to the y is a to the x plus y. Logarithms tell you exponents. And so if I'm taking the log of that, that's the same as taking the log of that. You had better get x plus y, okay? And here's a product, and in fact, just notice that's the same as like, okay, I should have made this log base A, whatever. It should be log base A. Some of the A's cancel. Stupid math stuff. Here's the rule. Okay, here's the rule. I can worry about the details later. Maybe I'll make a log video. If someone asks me to, I will. But otherwise, there's just tons of resources on logs. And I hate math rules. I hate them. And then I want to talk about it. Okay, I'm going on a tangent. So here's the thing. Let's use that rule. This is equal to log base 10 of 2 plus log base 10 of h. And hey, look at that. This and this are the same. Okay? So if you double the molarity of hydrogen ions, let me just look up log base 10 of 2. Log base 10 of 2 is 0.3. Okay? So how does the pH change? Well, if the pH was 7, now the pH is 7.3, because I have to add 0.3 to whatever the old pH was, right? If the pH was 1, now the pH is 1.3. I've doubled, in some sense, like you might want to say, I doubled how acidic this is. There's twice as many just protons floating around, baby. Doesn't matter. You increase the pH by 0.3, okay? So the pH did not double. I guess it would. Oh, right. Sorry. There's this this negative sign, so it actually decreased by 0.3, which makes more sense. If you add protons, you're getting more acidic. Okay, whatever. The point still stands. Logs are not sensitive to change, okay? We doubled the input, and the output changed by 0.3, okay? You can 100-fold the input, and now this is a matter of comparing log 10 of some solution versus log 10 of a solution that is 100 times the molarity, okay? And we use the same thing. This is log 10 of 100. 100 is famously 10 squared, plus, right, I'm doing 100 and h, so log 10h. So whatever your initial pH was, here it is. Okay, it should be negative. Fine, I'll make it negative, negative, get rid of this. Cool. Whatever your original pH is, how much does it change? Well, what's this? Well, okay, log. What is the exponent on 10 for this number? Oh, it's 2. So it changed by 2. It got, if the old pH was 5, the new pH is 3. If the old pH was 7, the new pH is 5. Okay? You have to have 100-fold increase in the number of protons to become acidic by 2 pH units. Okay? Which, by the way, this is a unit conversion. There's molarity versus pH. Okay? Whatever. Okay, so another... Oh, right. Hey, fun fact. In 1950, there was 310 parts per million CO2 in the atmosphere, and the ocean surface pH was roughly 8.15, okay? And so the ocean water had some molarity of hydrogen ions in 1950, and that's what this number is trying to say. The hydrogen ions in the ocean in 1950. Okay, the current pH of the ocean is about this. Okay, so if we're trying to figure out, hey, how many hydrogen ions are that? That means we have to solve this thing. And, okay, how much has the molarity changed? The molarity of hydrogen ions in the ocean? Well, let's take a peek at this. So, all right, if we play around with this, what log is saying? Log is saying what power on 10, okay, so 10 to some power had better equal that molarity, H plus 2023. So today's molarity, or I guess last year's, whatever. And it turns out that power is negative, because there's this negative here, so I move it over, negative 8.05. Cool. Similarly, in the 1950s, that power would have been negative 8.15. All right, so we have new and old, and so now we can get like a percent change. Okay, so that's why I was doing this. So now I'm going to get my handy dandy computer here, and I have 10 to the negative 8.05 divided by 10 to the negative 8.15, and drum roll please. This is 1.25. I'm going to round a little bit and put 9, but it was 8, 9, 2, blah, blah, blah. Okay, so I'm just going to call this 9. All right. So what do we see? There's roughly 25% or 26% more hydrogen ions in the ocean. Okay. That's what this is saying, right? Some ratio. So, yeah. Wait, less. It's more. No, it's more acidic. Wait, if the current. Oh, yeah. More. Right. Lower numbers at higher pH. It's more acidic. Whatever. Okay. There's roughly a 25% increase in the hydrogen ions in the ocean. And if we were just curious, like, hey, does this reflect what's going on in the atmosphere? So I could take the old parts per million in the atmosphere and multiply it by this. So 310 times 1.259. And if I do that, times 310 is equal to, I get roughly speaking 390 parts per million. And so yeah, like it turns out, so currently there's actually about 410 parts per million, but like ocean acidification is tightly linked with the CO2 in the atmosphere, and this is why there's coral reefs bleaching and stuff like that. Climate change is real. Pay attention. Okay, so cool. I'm going to stop the video here. We'll make another video talking just about inverse functions, and then I'll probably actually put this one before the other. I don't know. We'll see.